All right, guys, we are moving into section 1.3, where we're going to look at some graphs of function. There's a little bit of this stuff we talked about in the last lesson, and then we will look at some new stuff, maybe even some stuff you haven't seen before in another class. So here's what we're going to be able to do. By the end of this lesson, we're going to find the domains and ranges of functions. Use the vertical line. That's something we talked about last time, the vertical line test for functions, so that's no problem. Determine intervals on which functions are increasing, decreasing, or constant. Determine relative maximum and relative minimum values of functions. We're going to spend a brief amount of time on step function and other piecewise defined functions. And then lastly, we're going to identify even and odd functions. Okay, so let's go ahead and get started. Looking at the graph of a function. And we really talked about this last time. I'm not even going to go through that. That's sort of a little bit confusing. What we're talking about is using the graph of a function to find what it wants to find the domain of f. Remember, the domain is the same as the x, or the domain is how far this graph stretches on the x-axis. We want to find the function values of f-1 and f2 using the graph rather than an equation, right? So last time we had maybe f of x equals x plus 2, and you're asked to find f of -1, and for there you would just plug -1 in for x and get the function value at -1. Okay, but we're going to use the graph here. Whoops, that's not going to work. I can't erase it, but I can back out of it. All right, so first of all, the domain of f. So what we've got to do is look at this graph that ends right here, goes up as a parabola, and then it ends right here, but does not include that point right there. And this is where we're going to use that interval notation that we talked about before, last lesson. The domain is how far to the left this graph goes and how far to the right. So if we go to the left, it goes to, right here we drop down, it goes all the way over to -1. And since this is a solid point, it includes -1. So remember, we put the bracket to include -1. So this graph runs from -1 over to, right here, 4. Now, because it's an open circle, that means this comes as close to 4 as it can get without ever actually getting to 4. So it doesn't include the point x equals 4, or the value at x equals 4. So we would say that the domain on an interval goes from -1, including -1, up to 4, but we're going to put the parentheses because it does not include 4. All right, so that's all it is to find the domain. All right, so the function values, f of -1 and f of 2, since we don't have an equation, what we have to do is we have to look at the graph. Remember, this is the f of x, so this is my x value of -1. So where is x -1 at? Well, right here is -1 on the x-axis. All right. If I want to find its function value, what I do is find out where the graph meets -1, and it's right here at the point -1, -5. When x is -1, y, or the f of -1, is -5. So that's how I can use a graph. I go to that x value, and then I intersect the graph at that x value and find that point. What's the function value at 2? Well, here's 2. Where's the graph? Intersect x equals 2 at right there. Well, what's the y-coordinate when x is 2 for this particular graph? Well, the y-coordinate is 4, so that means f of 2 equals 4, right? If I wanted to know f of 3, Well, here's 3. What I would do is I would go up to this point right there, and it looks like it's at about 3, 3, right? So I would say, based on this graph and what I'm seeing, the function value at 3 is positive 3. Okay, so that's how you use a graph to find different function values. Now the last part is the range, and the range is how far it goes up and down, right? Range is always associated with y. So it's how far does this graph go up and down? Well, it goes down to here, it goes up to this point. So what's the lowest y value? Well, it is -5, and it includes -5, right? Because it's a solid point right there. So the low point, oops, come back, is -5, and then it goes from -5 up to +4, includes the point +4 because that is a solid circle. So we go from -5 to 4 is the range, right? And we always want to go from smallest, so we're going to go from bottom to top when we're writing it in interval notation. All right. If that were to carry on forever, remember that would be -infinity up to the top point. Obviously, a parabola bounces back down. It doesn't keep going up forever. All right. Normally, parabolas go down, and like in this one, would keep going. The domain would be all real numbers, but this particular problem cuts it off. It puts the dot there and the open circle there. So it's only really looking at a section of this parabola. Okay. That's how we can find the domain, by looking at a graph. We can find function values looking at the graph, and the range by looking at a graph. All right. And that's just an explanation of the same things that I just talked about. So we're going to slide on past that. All right, we talked about the vertical line test last time, so I'm not really going to talk about it, right? If you have a graph and you take a vertical line through a graph, if it ever is intersecting the graph more than one spot at a time, then it's not a function, right? You can't have points directly above and below each other for it to be a function, right? So this one, because there's points directly above and below, it fails that vertical line test. This is not a function, right? And this one, at no point would that vertical line intersect that at more than one spot. So this one, yes, is a function. But we talked about that last time. So I'm going to move on past that. All right, so now increasing and decreasing functions. All right, all this is we're taking a graph and we're going to put in interval form the sections of the graph that are increasing as x gets larger and or decreasing as x gets larger. So all that is if we have this graph right here. All right, it's always as x is increasing. That means we're going from left to right. As we move across the graph from left to right, x is increasing, right? -2, -1, 0, 1, 2, 3, 4. So as we go to the right, if the graph is going downhill, that is considered decreasing. If it's horizontal, that's considered constant. If it's going up, that's considered increasing. So this particular graph, if I were to answer anywhere is it decreasing, I'm going to just write right there. Over what intervals is it decreasing? Well, the intervals, we're talking about the x values. Right here is where it starts at -2, including -2. And it's decreasing till we get down to 1. And on intervals, I don't think it really matters if you include the point or not. I would say actually we probably would use a parentheses right there, but I don't think it's that big a deal. It was constant. from 1 to 2. From 0. Right here, the x value is 0 to 2. And then it is increasing from 2 to 4. And I'm going to include 4 there. Okay, so that's what we're looking to do. All right, is label when is it increasing, when is it decreasing, so on and so forth. All right, so let's move on. And this is the actual mathematical definition. To me, this sort of confuses it. But let me explain. A function is increasing on an interval for any x1 and x2 in the interval. x1 is less than x2 implies f of x is less than f of x2. All right, basically that means it's going uphill. That if the x is smaller than the x2, so this point smaller than this point on the x, that means on the y that this point is lower than that point. So it would be increasing. Opposite for decreasing. Okay? If x1 is less than x2, that means the f of x or the y is greater than that one, so it's going downhill. And then they're equal. All right? So this is a little bit of some mumbo jumbo, is what I like to say, because it's a little harder to understand than looking at the graph. It's pretty easy to understand. That's going downhill. That's decreasing. That's staying the same. It's constant. This is going uphill. It's increasing. All right. So determine the open intervals on which the function is increasing, decreasing, or constant. All right. So notice, and this is what I was talking about a minute, open intervals, that means we're going to have parentheses on our intervals, not including the point. We're just talking about the area that it's increasing. All right. So if you look at this one, this is a graph that it continues that way forever and it continues this way forever. All right. And for what interval is this? And it looks like it's a little tough to tell, but does it stop increasing right there? It almost looks like it's constant right there. Okay. But I don't think it actually does. Once you zoom in on that, it's actually ever so much increasing each time. So this is a case where one is increasing. It's still increasing there very slowly, but it's still increasing. Then it starts increasing again faster. So this is increasing the entire time. So if we were wanting to write it in an interval, we would say it is increasing from negative infinity to infinity. The whole line, it is increasing. Okay. Now this one, we can see that it starts here. This is going down, so it's going down forever. So it's coming from way down here, and it is increasing till it gets to that point right there. So what interval is that right there that it is increasing? All right, so we're going to write it as increasing, and where is it decreasing? Well, it is increasing on the interval from negative infinity, right? Because this is going to keep down and out forever. So it's coming from x. It goes forever. So we're coming from forever away to here, and it's increasing till we get to right here, which is x at -1. So I'm going to put -1. It's increasing. All right. Where else is it increasing? Well, notice it decreases to here once we get here. Now it starts increasing again. I didn't draw that very good. And then it keeps going forever and ever. As you go further and further, it keeps going up and up. So it is also increasing. Right here is the x value of 1, 2, and forever. Infinity, right? As you go this way forever, it's going to continue to go up. Now, what is the interval that it is decreasing? Is from here to here. That is going downhill right there. So what is that interval? That is an x value of -1 to the x value of 1. It is decreasing. So that's all I'm doing is I'm labeling at what intervals is it increasing, what intervals is it decreasing. Okay. Let's look at this. This is a piecewise function. All right. So when x is less than 0, it is going and using this formula. From x of 0 to 2, it's using this horizontal line, and then it's going here. So where are we increasing? Well, right, this is going to go forever. So as I go to the negative direction to infinity, it's going to continue to go down this way forever. So basically, it is coming up from negative infinity all the way up to x equals 0. So it is increasing from negative infinity to 0. It is constant from right here to right here, right? That's the x value, right? We're only on intervals, we're only looking at the x values from the x value of 0 to the x value of 2. And once again, we're using parentheses because we're not including the point there because it's only staying constant till it reaches that point. And then it is decreasing, right, from here, and that's going to go forever. So as I go to the x towards infinity, it's going to continue to go down forever. So it is going down from 2 to infinity. All right. So that's how we're going through and labeling how it's increasing or decreasing or constant. All right. Using our interval notation. All right. Notice parentheses, not using any brackets. We're talking about there. All right. So now when we have parts that are increasing and decreasing, we have what are called relative minimum and maximum. We know what minimum and maximum. Minimum means the least, maximum means the most. So this isn't going to be very difficult. All right. Now this makes it seem a little bit difficult. It says a function value f of a is called a relative minimum of f where there exists an interval x1 to x2 that contains a such that x is in between those two. The x-coordinates in between those two in that interval, and f of a is less than f of x. That's a relative minimum. Relative maximum is just the same. All right. Now, can you wrap your head around that? This doesn't really even make a whole lot of sense to me. I understand it, and I can work through it, but let me show you what that really means. Relative minimum, relative maximum simply means this right here. On this interval between here and here, this is the lowest point, so this is considered a relative minimum. Basically, the bottom of the curves. Where a graph goes from decreasing to increasing is a relative minimum. Then, if you look at this interval from here to here, it bounces. It's increasing and then starts going decreasing. This is a relative maximum. It's the high point between an interval, right? If I was looking anywhere between these two x values here and here, that's a relative minimum. I mean a maximum. Here is another minima. It's at the bottom, right? Changes from decreasing to increasing. This one then changes from increasing back to decreasing. So this is a relative maximum. All right. So relative maximum and minimums are just high points and low points within a graph. All right. Now we're not talking about the absolute highest point on the graph. We're talking about within certain intervals. So if I were just looking at this interval from here to here, this is a relative maximum. If I was looking at the interval from here to here, between here and here, this is a relative maximum. I'm looking between here and here on the x-axis. That's an interval, say from 0 to 2. This is a relative minimum. All right. So if we want to punch this It says use a graphing utility. That means basically a graphing calculator. And they went ahead and put the picture of it right here. Use a graphing utility to approximate the relative minimum of the function given by this right here. Okay. Well, the relative minimum is the low point of the graph. This is a bounce point. All right. Now, if we were to estimate that, now if I'm just looking at this graph right here, it's going to be kind of hard to estimate. Okay, because the x value looks like it's right about here, and I'm not exactly sure where that is. Okay, but I believe, let me pull up my calculator. Let's see if I can figure out how to do this. Here we go. Where is my TI? Smart View. All right, so I believe the calculator is going to pop up. There it is. And I'm going to type that in to the calculator in the graphing part. So we're going to look at the graph. Let me clear this out. And let me see if I can remember what that was. I believe I've got it here in the book. Yes, 3x squared. So we were looking 3x squared minus 4x minus 2. All right, we were looking at the graph, and there it is. Okay, it's kind of tough to tell where exactly that minimum is, what's its ordered pair. Okay, it's a little bit less than the x value of 1. I can tell that, but I'm not exactly sure. But what we can do on this calculator is I believe if we hit second trace, all right, second trace, notice there's a minimum and a maximum. So minimum is what we're looking at here, right? Because that went down and back up. So that's a minimum. So I'm going to hit 3. And then notice it puts a little blocking X. I just have to make sure that X, I have to create my interval. That doesn't matter the exact interval. It's just the interval has to start on one side of the minimum and has to end on the other side of the minimum. So I'm good there. I hit enter. And then I arrow over to the right, and it takes it to the other side of that. I hit enter. And then I hit enter one more time, and then it gives me a good estimation right there. You can see at the minimum is 0.6666663. The y coordinate is negative 3.333. So this is at about 0.7 comma negative 3.3 is the relative minima, or the relative minimum. That's just an approximation right there on that using my calculator. Okay, so we said that is at about 0.7 comma negative 3.3. All right, and that's what that's good enough. It asks us to approximate. Okay, sometimes you'll be able to see exactly, sometimes you won't. All right, and that's what I said. They use the zoom and trace. They use zoom and trace. I think it's easier to go ahead and use your minimum like we did, and it gives us that point. There's no reason to trace and try to predict where the middle is. So I'm saying using that minimum point, which, if you remember, was second trace, and you can find relative minimums and you can find relative maximums right there on our calculator. Okay. So tells us later we'll be able. So at some point we'll find the exact. Basically, when we're talking about graphing parabolas and stuff like that, and looking at some graphs of things like that, we'll be able to find the exactly instead of an approximation. All right. I'm going to talk about step functions real quick. They're a little bit confusing, but I think we can get it figured out. And piecewise defined functions. So we're not going to spend a lot of time here, but and I don't really want to talk about this. What we're talking about, the greatest integer function, okay, is sort of weird. All right, and you could do it on the calculator, but it's a bit of a process. We're not going to get into that right now. But what it actually is if I have f of x equals, and it's this like a bracket with an extra line in it. All right, and this stuff right here sort of makes it a little bit more complicated. But what this means basically is if I have whatever f of whatever is, all right, if it's an integer, if I have f of 3, then this greatest integer of 3 is just 3. And basically anything 3 point whatever, 3.5, is if it has any extra thing before you get up to the next integer of 4, okay, you basically, the x value is 3 point anything, as you drop off any of the decimal and it's just 3, you're left with that integer. If I have f of 3 3/5, its value is just 3. It switches to 4 once I get to f of 4. If I have 4.3 repeating, right, the x value, I just drop everything and keep the integer. Okay? And let me double check something real quick. Yeah, that is correct. So what happens is this is what the graph looks like. If I were to have, let me see if I can draw a graph real quick. Draw another line. All right, so if we have 1, 2, 3, 4, 1, 2, 3, 4, the way it looks is if I have the x value of 1, right, that means it is 1. Y is 1. If I have the x value of 1.5, y value is still 1, right? We drop off the decimal. All the way up to 1.9999999 is going to be that right there. So what I have is I have just a little section of a straight line right here. Now, once I get to 2, all right, what it means is this line goes all the way up to 2, so I got to leave an open circle. And then at 2, it turns into the y value of 2. 2.5 is going to be 2. I drop off the 0.5. 2.9999 all the way up to there. So what I have is I have a line that starts right there and goes to 3, an open circle. Once I get to 3, the y value is 3. 3.1, 3.2. I'll drop off the points all the way out till I get to 4. And so what we have is this graph that looks like this right here. And it keeps going right here, right? It'll be down here. So this is why it becomes, because it looks like stair steps. Okay? So in your assignment tonight, you're going to look at one that has something like this right here, f of x equals, and this is the symbol for it, 2x. All right? So that means f of 1 is basically, I put 1 in for there. That is 2. 2 times 1 is 2, so that's going to be 2. If I put in f of 1.1, all right, that's going to be 1.1 times 2 is 2.2. I would drop off the 0.2, so it's 2 is still 2. Now the difference here is because I'm putting 2 there, once I get to f of 1.5, right, 1.5 times 2 is 3 without a decimal, so it is now 3. Okay, so basically these little lines are going to be cut in half because once I get to 1.5 here, it hops up to 3. So the little step lines are going to be shorter. And we'll talk later how to get that into the calculator, but right now we're not gonna talk about that. And I just wanted to introduce that. So there will be one problem on the assignment about this. If you have a little trouble, we'll talk about it as we're working on it. But I don't want to spend a whole lot of time on that right now. Here it's asking us to sketch a graph of a piecewise function. Okay, so I'm just going to do that real quickly here. Make sure we do that. So notice x is less than or equal to 1, which is right here, right? So that means let me get here's 1. On this side of the graph over here, all right, we're using this one. Once we get to this side, once we get past 1, over here, when x is greater than 1, we're going to use this equation. Okay, so notice how this happens is, so for this yellow part, from x equals 1 and smaller, all right, we're using the formula 2x plus 3. Well, that means when x, these are linear, so when I do x is 0, plug in 0 for x, I get 2 times 0 plus 3, which is 3. So I'll have the point 0, 3 is on there. So 1, 2, 3. This point is on that line. And then this includes 1, so I can use 1. So when I put 1 in there, 2 times 1 is 2 plus 3 is 5. So the point 1, 5 is also on here. So this yellow part of the graph is using this line right here. I didn't make it very straight, but I'm using that line. And this is a solid dot right here at 1 because it includes 1. Now for this one, I can use the point 1 also. And when I plug in 1, I get negative 1 plus 4, which is 3. So here, when x is 1, it's at 3. Now, what I have to do is at that point, I have to put an open circle because it actually does not include the point 1. And then I can go to 2 to find another point so I can draw this line when x is 2. X is greater than 1, so I'm going to use this. Negative 2 plus 4 is 2, so the point 2, 2 is on that line. So now I'm looking at this. So sketching this graph is on this side in the yellow section from infinity all the way up to x equals 1. This is the graph I'm using, this line right here. Once I get to 1, it changes to this one, which means here I go to this line. Right now, if I just had negative x plus 4, I would be talking about this line that continues here forever in both directions. But I'm only using that line when x is to 1. So this is like the dividing point. This is the point in which it's going to switch from one line to the other. All right. So hopefully that makes some sense there. All right. There's a little better drawing of it than my little sketch that I did. Here, open dot here because the x less than or equal to 1's with this top graph, which was this one right here. All right. All right, last thing we're going to talk about real quickly are even and odd functions. All right, and basically we're just going to define what even and odd are and show you how to look at a graph and tell the difference between an even and odd function, and also how to be able to do an even and odd function algebraically. Okay, so and the way they're talking about odd and even is by symmetry. A graph has symmetry with respect to the y-axis. If whenever x and y is on the graph, then so is the point negative xy. Basically what that's saying is if you have a graph that has a point on the left side of the y-axis and it is mirrored on the right side, And every point that's on this side is mirrored on this side. Every point that's on this side is mirrored on this side. So that when you connect the dots, you have a graph that is basically mirror images across the y-axis. Okay? So this is the point xy. This is negative xy. It's the same y coordinate, right? So if this was the point 2, 3, then this is the point negative 2, 3. All right? So graphs or functions that follow this pattern, okay, well, it doesn't say if that's odd or even. I get it confused. So let me make sure I get that. This is an even function. I wanted to make sure I got that straight. So whenever this is the case, right, that it matches up, basically the y-axis is a dividing line. If you folded this across the y-axis, this side would line up to this side exactly. This is what is called an even function. All right. All right. And we're not talking about in respect to the x-axis. I'm not exactly sure where that's coming from there. So we're going to skip this right now. I don't really like what that says. And a function whose graph is symmetric with respect to the origin is an odd function. Now what that means is if I have xy up here, that means the negative of x and the negative y, that point, the opposite of x, the opposite of y is also on. So anywhere I have a point down here, it matches up there. And you see them a lot with these types of things right here. This is called an odd function. All right, that it is, and it's usually this cubic graph that we look at that is an odd function. All right, where a point in this coordinate matches the point down in this coordinate. All these points match up all these points up here. Okay, that is called an odd function. All right, now if we were looking at, well, here's the graphs. All right, notice these symmetric to the y-axis. Okay, could fold it along the y-axis. It would lay on top of each other. This point is mirrored over here. This is an even function. All right, symmetric to the origin. The point xy is on here. The opposite of x and the opposite of y is also on that graph. This point, this point, this point matches this point. This is called an odd function. All right, notice a negative x makes a negative y. Here, a negative x still makes a positive y. Now, here, the x-axis, all right, we can't say odd or even here because now we are looking at something that is not a function, right? It can't be an odd or even function if it's not a function. That's why symmetrical to the x-axis does not make it odd or even, because it is not a function, okay? So that makes sense there. So even, odd, not a function. So you should be able to look at a graph and see if it's odd or even. The last thing is algebraically how to determine if it's odd or even. So notice what it says here. It says a function f is even when for each x in the domain that whenever you substitute negative x in for x, you get the function, the original function value, right? That's where the x side by side, the x and negative x still gives me an output of y for both of them. It is odd when I put in a negative x, I get the opposite value of the function, right? The negative x gives me the negative y. So let me show you quickly how this works. All right, so we have these three function values right here, and it wants to know, are these even, odd, or neither? So what we do is, let's take this one right here, g of x equals x cubed minus x. So what I'm going to do is I'm going to plug in negative x and see what I get. So this would be negative x cubed minus negative x. All right. Well, what is negative x cubed? Well, that's like negative 1 cubed. Negative 1 times negative 1 times negative 1 is negative 1. So negative x cubed is negative x cubed. All right. And then minus negative makes that a positive x. All right. Now, obviously, when I plug in negative x, I do not get this right here. If I were to plug in a negative x and it simplified back to what I originally had, what was that? That was an even, right? I plugged in negative x and I got what I originally had. So this, we know, is not even. All right. Now, the way we can tell if it's odd is if I can factor this negative out, right? Factor that negative out, and I would be left with x cubed plus x. Now notice, x cubed plus x is g of x, so this is essentially negative of g of x. And if it is the opposite of g of x, when I plug in negative x, it is odd. So this one is odd. All right. So that's sort of how you do it. If you plug it in, simplify it, and then if you can factor that negative out front and you're left with what g of x originally was, then that is an odd function. Let's look at the next one. H of x. H of x is equal to x squared plus 1. All right, I'm going to plug in negative x for x. So that's going to be negative x squared plus 1. Well, what's negative x squared? Negative 1 times negative 1 is 1, and x times x is x squared. So it simplifies to x squared plus 1. So when I substituted in negative x, I ended up with the exact same thing I started with. And this is going to make that one even. All right. If I were to look at the graph, this would basically be a parabola kind of like this right here, right? We can tell by the graph that's even. All right. And then let's look at the last one. F of x is equal to x cubed minus 1. So I'm going to substitute in negative x for x. And what I get is that is going to be negative x cubed minus 1. And now when I factor that negative out of it, I've got x cubed plus 1, which I started with x cubed minus 1. I ended up with a negative of x cubed plus 1. So this and this do not match. So this is not the negative of that. So this is an example that it is neither. Right? So if I substitute in negative 1 and I get the negative of the g of x or the f of x, what I started, that's when it's odd. If I substitute in negative 1 and I get the exact same thing I started with, that's even. And then if I substitute in negative and I get the negative of something that was not match up to that, this is neither odd nor even. All right. So that's just an explanation of that. And I think that is all we have. So I'll go ahead and assign 1.3, and we'll work through that the best we can.